Hello, in the first part of the video we proved that if we had some matrix here, this one here, M, with coefficients A, B, C and D, we could find an inverse matrix by just rearranging those coefficients in the matrix and having this 1 over the determinant out the front, and that would be the inverse matrix. And it's a bit like multiplication, that if I took a number and I multiply it by 5 and then I multiply it by 1/5, I always come back to my original number. So this is the equivalent that if I've got a matrix here M, then which was like equivalent to 5, then this inverse matrix, the M to the power minus 1, is the 1/5 matrix. Yeah. And that's really useful because if I was trying to solve the equation that we were looking at, that a matrix times our xy vector equals some constant, then we can find that unknown vector. Oops, there we go, that unknown vector, because we can take our inverse matrix and multiply it by our constant vector. There we go. And we also had to look at the fact that, of course, this determinant little multiplication here must be non-zero, and I'm going to now expand upon that and we'll have a look at how this works in practice. So let's look at the matrix we were looking at earlier was 3, 2, 4, 5. Yeah. And what I want to do is find the inverse matrix for that. Well, I've got two things I've got to do looking up here at the inverse. The first thing I've got to do is to find what this determinant value is here. Well, I'm just going to write those there, A, B, C and D. So AD is 3 times 5, then we're taking away BC, which is 2 times 4, so that's 15 minus 8 is 7. There we now know that this 1 over the determinant is 1 over 7. Yep. Second thing we need to do is to work out what the coefficients inside of the matrix, and we'll have a look. Let's just do a bit of comparison to see what happens. Well, let's look at the leading diagonal first. We started off with AD in that, and according to the inverse algorithm, that's becoming D and A. So what do? We're going to swap these two over. So the first thing I do is swap those two over. So 3 and 5 are going to become 5 and 3. Yep. And then in the inverse, we can see here that the B and the C is still in the same place, but the signs changed. So where it was B in the original matrix, it's minus B in the inverse. Where it's C in the original matrix, it's minus C there. So all I do is leave the values there and put a negative in front of them. So there we are. So that's what we do in the algorithm. We swap the two on the leading diagonal and change the others to being negative. So now I've got that. I can do a bit of tidying up, can't I? Because my ultimate version of that is that the inverse matrix is 1/7 of 5 minus 2 minus 4, 3. Yep. Okay, how can I use that to solve equations? Well, this is the simultaneous equation we started off with, and here's we rewrite that in matrix form. Here we go. In matrix form, I've got my matrix M that we've just found the inverse of. I've got my X vector, which is my xy, my unknowns vector, and I've got this constants vector on the side 9, 5. Yeah. And effectively I've written this equation here, and if I write the inverse of the equation, then X is going to be the inverse matrix times the constant. Well, let's just put those values in and do the calculation then. So there's my inverse matrix, there's my constant. I use my normal calculation multiplication method for matrices. So when I want to look at my top value in my resultant vector, I take my top row and I multiply it by my column vector there. So what am I going to do? I'm going to get 9 times 5 and 5 times 2. So 5 times 9 minus 2 times 5. What have I got there? I've got 45 minus 10 is 35. So there's 35. If I do it for the lower row, then I've got 4 times 9 and 3 times 5, haven't I? So I've got minus 4 times 9 is minus 36, add 15, I've got minus 21. So there we are. I've put those back into the vector like that. But of course I've got my 7th out the front, as a factor, and I can now bring that back in and do a division, can't I? So 35 divided by 7 is 5, and minus 21 divided by 7 is minus 3. So there we have it. There's our solution. Yeah, if I wrote that as a the xy, that's a vector, isn't it, that x there? There I've got x equals 5, y equals minus 3. So that's really useful and quite a quick way to do the calculation, isn't it, to find the solution. Okay, I'd like to expand on that and start to think about what's going on here and why that works and learn a bit more from it. So if I take, there's the equation we just worked with, isn't it? We started with that. Now what happens if I pre-multiply that equation by the inverse matrix, yeah? There we go. Yep, so it's still an equation, isn't it? Because I've multiplied both sides by the same thing. Now on the right-hand side, in effect, I've got what we looked at earlier in the purple equation was the x, the unknown vector, yeah? But let's have a look at what's happening on this left side. I've got m minus 1, the inverse matrix times the matrix, and then times the vector. So let's do this part first, because the law is distributive. And let's do this calculation. So if I want to find inverse matrix times the matrix, I'm just going to write it out, yeah? There's the inverse matrix, there's the matrix. Now let's do the calculation. Well, what's important here is to start looking at each of the terms. So let's look at the coefficient on the term in the top left. So let's find that one. Well, what do? We take the top row and we take the left-hand column. There we go, and we multiply them together. The coefficients there. So what have I got? I've got dA minus BC, yeah? dA minus BC. And what's interesting is if we do the same thing, I'm going to do the bottom right here. Let's have a look at this one here, because there's something significant about these two. They're connected. So what am I going to get for that? Well, I'm doing the lower row and the right-hand column. So I've got minus CB plus AD, and that's that one there. Now you may have noticed that if I rearrange these and change the order of them, the DA minus BC is of course the same as AD minus BC, and if I do look at the bottom right, then I see that it's minus CB plus AD is actually the same as AD minus BC. So both of those values are the same. And what's even more significant is they are the determinant. They're the same as this value that we put out the front as 1 over. So if I bring that inside, I've got AD minus BC rather, divided by AD minus BC, which is 1. And I've got the same in this corner, in the bottom corner, haven't I? That AD minus BC divided by AD minus BC. So that's going to be 1. Of course, that's all going to be 1 as long as AD, B and C are not all 0, but that would be a meaningless step, wouldn't it? Because any number times by 0 is 0. So here I've got 1 and 0, yeah, and it doesn't matter what AD and BC were, we're always going to end up with 1 and 0. Okay, now let's have a quick look at the other corners. I'm just going to rub that out so that we can all see what we're doing, and let's have a talk about the other corner, the other diagonals. And on the other diagonals, let's have a look up here in the top right, yeah? So let's work this one out. Well, I'm taking the top row and the right-hand column, I'm multiplying them out. So I've got DB there, and I've got minus BD there, yeah? Hang on, what's DB minus BD? Well, it's 0, isn't it? Let's have a look at the bottom left. Well, to get this one here, this term here, I've got to take the bottom row and the left-hand column, and I'm going to multiply them out. And I've got minus CA and I've got AC there. So minus CA plus AC is, of course, 0. So what do we find then? That the inverse matrix times the matrix always comes out to this matrix 1, 0, 0, 1. Okay, well, what does this matrix do in practice? Well, I've got the matrix and I've got x, y, so I'll see what it maps any point set of x and y's to. And because it's a 2, 2, it's a 2, 2 times a 2, 1, I always get, again, I'm just going to get a vector out onto a 2, 1 vector. Let's see what it is. Well, what am I going to get for my top value in my vector? Well, I'm going to take the 1, 0 and the xy, so I get 1x and 0y, so that's x, isn't it? What about the bottom? I've got 0, 1, and it's coefficients of the xy, so I get 0 x's and 1 y, so I just get y. So what's this telling us? Well, it's telling us that if I take this matrix here and I multiply any vector by it, I always come back to the same vector. So this is the equivalent to ordinary multiplication of 1 times x will always be x, any number, wouldn't it? Probably better to use an n for number at this point. 1 times any number will equal the same number, won't it? So we call this the identity matrix. This 1, 0, 0, 1 is the identity matrix because it always maps any point x, y back onto itself, any vector onto itself, or any matrix back onto itself. And it also has this identity goes with it then, that the inverse matrix times the matrix will always give you the identity matrix, as long as our original matrix is not the 0 matrix. If we start off with 0, 0, 0, 0, which we call the 0 matrix, yeah, then of course this all becomes trivial, doesn't it? Because 0 times 0 is always 0, etc., blah, blah, blah. Okay, what's this mean in practice in terms of geometry? Well, these two simultaneous equations are actually two straight lines, aren't they? And if we draw those two straight lines and then we solve these simultaneous equations, what we're actually doing is finding the point of intersection of two lines. Yeah. And in this case, I'm interested in what the determinant does to all this because it's quite important. My determinant is AD minus BC, so what have I got? I've got 3 times 5 minus 2 times 4, yeah, which gave us 7. And that actually implies that there is an intersection here. What we're actually doing here is seeing that we've got different gradients going on. Okay, that's what it's telling us. We've got different gradients, isn't it? Because 3 over 2 is minus 1.5 and 4 over 5 is minus 0.18, isn't it? So that's 0.18 and that's 1.5, isn't it? It's our gradient, so they're both negative, aren't they? And they're different. And we'll just have a look at what happens if they're not different and what it does to AD minus BC. Okay, so let's have a look at this example on the left. Here, we effectively got two parallel lines, haven't we? Because they've got the same gradient, minus 1.5, but they've got two different intercepts, yeah? So in this case, AD minus BC is 3 times 2 minus 2 times 3, yeah? 3 times 2 minus 2 times 3 equals 0. So our determinant is 0 here, yeah, on this one. And there are no solutions, are there? Because there's no intersection. These two lines are parallel and they never meet. So there's no solutions to that one, yeah, when the AD minus BC equals 0. This is where the problems start. Okay, let's have a look at the right-hand one here. Well, these appear to be two different lines, don't they, the way I've written them, but they are actually the same line, aren't they? Because this one's just writing the same equation multiplied by 2. So what happens to the determinant here? Well, I've got 3 times 4, take away 2 times 6. So again, my determinant is 0. And here we have another situation where we don't have a single solution, yeah, because these are the same line, so I've got a whole line of solutions. So I've got an infinite number of solutions on that line, haven't I? In this case, I've got no solutions, yeah. Here, I've got solutions. I've got a whole line of solutions, haven't I? So that's the importance of this determinant, because if this determinant is 0, we know we don't have a single solution like we do up here, yeah. There's our, if we had a determinant of it's not 0, we get a single solution, and if the determinant is not 0, we end up with these other situations there. So in summary, this is where we got to, isn't it? We've looked at the fact that we can use calculating an inverse matrix, so we can take our basic equation and we can effectively rearrange that equation using the inverse to find our x value that we wanted to know, our x vector, by using the inverse matrix there. So effectively we've avoided division by using an inverse multiplication, yeah? So rather than doing 5 divided by 5, we've done 5 times 1/5, yeah, and got rid of it, and therefore found our values that way. So hope that's of use, and best of luck.